time travel, cosmic monsters devouring worlds. But pause for a moment and let this sink in. This is not imagination. This is not a Hollywood invention. This is real. This is observable. This is measurable. This is a black hole. Black holes stand as some of the most enigmatic, powerful, and unsettling objects in the entire cosmos. We cannot see them directly, they emit no light, reflect no light, allow no light to leave their grasp. Yet their invisible presence sculpts entire galaxies, influences the birth and death of stars, and forces us to confront the deepest questions about space, time, gravity, and the nature of existence itself. They push science to its absolute limits, demanding new theories, new observations, and new humility in the face of what we still do not fully understand. But what exactly is a black hole? How does something so extreme come into being? Who first dared to predict their existence, and how did we finally prove they were real? And perhaps most importantly for anyone gazing up at the night sky, should we fear them? Could one ever threaten Earth? Let us begin this journey together, step by step, from the fiery death of a star to the silent edge of eternity. Prepare to look into the abyss and see what looks back. Every black hole begins its existence as something familiar and beautiful, a star.
Gravitational pull.
Stars are not eternal. They are born in vast clouds of gas and dust, ignite through the miracle of nuclear fusion, and shine for billions of years by converting hydrogen into helium in their cores, releasing energy that pushes outward against the relentless inward crush of gravity. This delicate balance, fusion pressure versus gravitational collapse, is what keeps a star stable, whether it is our modest sun or a colossal supergiant. But not all stars are created equal. The fate of a star is determined almost entirely by its mass at birth. Stars like our Sun, about one solar mass, will eventually exhaust their fuel, puff into red giants, shed their outer layers as planetary nebulae, and quietly fade into white dwarfs, dense Earth-sized remnants supported by electron degeneracy pressure. Now consider stars far more massive, those born with 8 to 20 times the Sun's mass or more.
Here we see the telltale sign of a stellar
These
black
behemoths
hole.
burn through their fuel at ferocious rates, living fast and dying young, often in just a few million years. When the core's hydrogen is depleted, helium fusion begins, then carbon, oxygen, and heavier elements, each stage hotter, faster, and more unstable than the last. Eventually, the core attempts to fuse iron. But iron fusion does not release energy, it consumes it.
As we approach
The outward
galactic
pressure
core,
vanishes in
we
an
see
instant.
the engine driving its dynamics.
Gravity,
A
which has been held
supermassive-
at bay for the star's entire life, suddenly wins. The core implodes at a fraction of a second, collapsing from thousands of kilometers across to a sphere just tens of kilometers wide. Temperatures soar to billions of degrees. Neutrons form in a rebounding shockwave. The outer layers, still falling inward, meet this rebound and are blasted outward in one of the most violent events known, a core collapse supernova. For days or weeks, the exploding star can outshine an entire galaxy. What remains at the center depends on the original mass. If the core remnant is between roughly 1.4 and 3 solar masses, neutron degeneracy pressure halts the collapse, forming a neutron star, an object so dense a teaspoon weighs as much as a mountain. But if the core exceeds about 3 solar masses, even neutron pressure fails. Collapse continues relentlessly. Matter compresses smaller, denser, until it reaches a point of no return. At that instant, a black hole is born. A black hole is not a hole in the conventional sense, not an empty tunnel or void punched through space. It is a region of spacetime where an extraordinary amount of mass has been compressed into an infinitesimally small volume, creating a gravitational field so intense that escape velocity exceeds the speed of light.
Oh my God, we did
Nothing,
it!
no matter, no radiation, no information, can break free. The defining boundary is the event horizon, a perfectly spherical surface for non-rotating black holes, marking the point of no return. Cross it, and all paths lead inexorably inward. From outside, the event horizon appears as an absolute black sphere, often surrounded by a glowing accretion disk of superheated gas spiraling in, emitting X-rays, radio waves, and visible light. The black hole itself remains invisible. We detect it only through its effects on nearby matter and light.
The relativity of time becomes apparent.
At the
While
very
our
center
time
lies the
moves normally,
singularity, a theoretical point, or for rotating black holes a ring of infinite density and zero volume where spacetime curvature becomes infinite. Here, general relativity predicts a complete breakdown, densities become infinite, tidal forces tear apart any infalling object down to subatomic scales, and our current laws of physics cease to apply. Quantum gravity theories, still incomplete, suggest the singularity may be avoided or resolved, perhaps into a Planck scale structure, but we do not yet know. The interior beyond the event horizon remains forever hidden from external observers. Black holes are not uniform. They span an astonishing range of masses and scales. Stellar mass black holes, 5 to 100 solar masses, are born from the core collapse of massive stars. Event horizons are just a few to tens of kilometers across, smaller than many cities, yet contain several suns worth of mass. Cygnus X1 was one of the first confirmed candidates. Intermediate mass black holes, 100 to 100,000 solar masses, are harder to detect, possible in dense star clusters or from mergers. Recent gravitational wave detections hint at their existence. Supermassive black holes, millions to tens of billions of solar masses, reside at the hearts of most large galaxies. Sagittarius A star, the supermassive black hole at the Milky Way's center, has a mass of approximately 4.3 million solar masses. Refined estimates from Gravity and Event Horizon Telescope collaborations as of 2025, with an event horizon roughly 24 million kilometers across, about 17 times the Sun's diameter. The 2022 Event Horizon Telescope image of Sagittarius A star, released after years of processing, showed its blurry, flickering ring due to our vantage point and the dynamic gas environment. M87 star, imaged in 2019, is much larger at about 6.5 billion solar masses. Primordial black holes, hypothetical, asteroid mass to stellar mass, possibly formed in the extreme density fluctuations of the early universe post-Big Bang. They remain theoretical but are candidates for dark matter components if microscopic ones evaporated via Hawking radiation long ago. No confirmed detections as of 2026. Black holes were once pure mathematics. In 1915, Einstein published General Relativity, describing gravity as the curvature of spacetime. Within months, Carl Schwarzschild found the first exact solution describing a non-rotating black hole, the Schwarzschild metric. Einstein and others initially dismissed physical black holes as mathematical curiosities. Surely nature would prevent such extremes.
On the left, Hollywood's dramatic
The term black
interpretation.
hole was popularized by John Wheeler in
precise reality
1967.
of a scientific simulation.
Early evidence accumulated indirectly. Cygnus X1 in the 1970s showed a massive invisible companion pulling material from a blue
Did you see
supergiant.
that X-ray flare? That is the
Orbital
most
dynamics
amazing
of
thing
stars
I've
near
ever
the
seen.
galactic center in the 1990s to 2000s, led by Andrea Ghez and Reinhard Genzel, Nobel 2020, proved an unseen 4+ million solar mass object, Sagittarius A star. Breakthroughs came rapidly. 2015's first gravitational wave detection,
Look at the energy signature. It's off the charts.
GW1500914, by LIGO,
The
two
data
stellar
is
black
stable.
holes
73
merging
sigma,
1.3
confirmed.
billion light-years away. 2019's Event Horizon Telescope image of M87 star. 2022 Sagittarius A star image. By 2025 to 2026, dozens more mergers, refined mass measurements, and jet studies continue to confirm and refine our models. Near a black hole, gravity warps spacetime so severely that time dilation becomes extreme. To a distant observer, anything approaching the event horizon slows asymptotically, appearing to freeze just outside, redshifted to invisibility.
The very fabric of space-time.
From the infaller's perspective, time flows normally until tidal forces, spaghettification, stretch and tear the object apart. Light emitted near the horizon loses energy climbing out, gravitational redshift, shifting from blue to red to infrared to radio until undetectable. In 1974, Stephen Hawking combined quantum field theory with general relativity, predicting black holes emit thermal radiation due to virtual particle pairs near the event horizon. One escapes, the other falls in, reducing mass. Tiny black holes evaporate quickly, stellar mass ones take 10 to the 67 years, supermassive ones 10 to the 100 plus years. This resolves some information paradoxes but raises others. The black hole information paradox remains under active research in 2026. Supermassive black holes regulate galaxy formation, their feedback jets quench star formation, preventing overgrowth. They are not cosmic vacuum cleaners, their gravity acts only at close range. The nearest known stellar black hole is about 1,500 light-years away. Sagittarius A star is 26,000 light-years distant. Earth faces zero danger. Black holes humble us. They reveal how small we are in cosmic scale yet how powerful human curiosity can be. Every discovery, from Schwarzschild's math to the Event Horizon Telescope images, uncovers new mysteries. The universe is not finished teaching. Black holes are among its most profound lessons. So keep wondering. Keep exploring. Because the universe is still waiting and the abyss still has secrets to share.